A very good morning to everyone. My name is Chaitanya Mahamuni and I will be delivering a presentation on the special topic Study of Metamaterials as an Emerging Technology in Microwave and Millimeter Wave Wireless Communication. The supervisor for the investigation of work being Dr. KTB Reddy. This is a brief outline of the presentation. Objective. The main objective of the special topic is to study metamaterials as an upcoming trend and new frontier of science and technology. To investigate the various areas in the field of wireless communication where metamaterials can be effectively used. Lastly, a case study, improvement in the performance of antennas using metamaterials. Literature review. The literature review consists of the following points: the shortcomings or the limitations of the existing materials, how these shortcomings can be overcome by using metamaterials, application of metamaterials, the application of metamaterials in the field of wireless communication. Limitation of existing materials. Inability to control macroscopic parameters. The macroscopic parameters of any electromagnetic material are its permittivity and permeability. The dielectrics have positive permittivity only. The metals show negative permittivity at optical frequencies. The plasmas have negative permittivity in certain frequency bands. However, the permeability remains positive in both the cases. The ferromagnetic material shows negative permeability at microwave frequencies. The possibility of occurrence of negative permeability in the terahertz frequency range is very rare. So, the naturally existing material with simultaneously negative permittivity and permeability is not yet found. Thus, the control over the macroscopic parameters is not possible in case of naturally occurring media. This can be achieved using metamaterials, but how it can be achieved using metamaterials we will see in the next slide. Classification of metamaterials. Depending upon the electrical permittivity and permeability, metamaterials can be classified into four types. The first is ENG type of material. ENG stands for epsilon negative. These type of materials are called as ENG materials because the electrical permittivity is negative, that is, value of epsilon is less than 0. Plasmas can be classified into this type. What are plasmas? The plasmas form the fourth state of matter where the properties of the matter are altogether different as compared to the other three states of matter, that is solid, liquids and gases. A plasma can be created by heating a gas molecule or subjecting a gaseous substance to electromagnetic radiation. The second type of material is DPS material. DPS stands for doubly positive material. These type of materials are called as DPS materials because both electrical permittivity and permeability are positive, that is, values of epsilon and mu are greater than 0. Conventional dielectrics can be classified into this type. The third is MNG type of material. MNG stands for mu negative. In these type of materials, the permeability is negative, that is, value of mu is less than 0, so they are called as MNG materials. The gyrotropic magnetic materials can be classified into this type. The gyrotropic magnetic materials are the materials altered by the passage of quasi-static field. The term quasi-static comes from thermodynamics. It is a thermodynamic process which takes place in finite long time to happen. It is a reversible process. The fourth is DNG type of material. DNG stands for doubly negative material. These type of materials are called as DNG materials because the electrical permittivity and permeability both are negative. Such materials are not found in nature, but they can be synthetically produced. All the electromagnetic metamaterials fall in this category. Why metamaterials? Improvement in the macroscopic behavior. As already stated, the major limitation of the naturally occurring materials is inability to control the macroscopic parameters like permittivity and permeability. This can be overcome by using metamaterials. But how? Metamaterials possess their properties not because of the type of material but due to their structure. Hence, the desired electromagnetic properties and the response of the system can be achieved. Allows designer with a large number of independent host parameters. Metamaterials are fabricated by embedding an artificially fabricated inclusion in a specific host medium. This provides a designer with a large collection of independent host parameters like shape, size, inclusion, and composition. The design parameters play an important role in getting the results. The shape and inclusion are the most important parameters in the metamaterial processing. Enables manipulation of wave propagation. An engineered manipulation of electromagnetic waves through metamaterials is possible due to the electromagnetic possessed by them because of the structural arrangement of units. Simplify and improve the design of electromagnetic devices like antennas. The miniaturization and simplification of the design of the electromagnetic devices like antennas is possible by using metamaterials. We can design the antennas with dynamic change in radiation pattern, no moving parts, and phased arrays using metamaterial technology. Application of metamaterials. Superlens. The lens which go beyond the diffraction limit by using metamaterials is called as a superlens. The first superlens in year 2004 operated in microwave frequency spectrum showed a resolution 3 times better than its diffraction limit. The important application of superlens is super-resolution medical imaging. The optical superlens also broke the diffraction limit in optical frequency range and showed super-resolution characteristics. Cloaking devices. The action of making a physical object completely or partially invisible by passage of electromagnetic radiation through it is called as electromagnetic cloaking. The metamaterials can be used in the physical realization of cloaking devices. Acoustic engineering. The acoustic metamaterials are the type of materials used to direct, control, and manipulate the sound waves in the form of sonic, infrasonic, and ultrasonic waves as they travel through solid, liquids, and gases. Seismic metamaterials. These type of materials are used to counteract the effect of seismic waves on the man-made structures that exist near the surface of Earth. Metamaterials enabled application in wireless communication. Gain profile enhancement. The metamaterials can be used to achieve increase in the gain of antennas, but how we will see in the next section as a part of case study. Electromagnetic coupling reduction in MIMO systems. The MIMO systems, that is multiple input multiple output systems, are usually operated in the lower half of millimeter wave frequency spectrum. The MIMO systems comprises of antenna elements which are placed very close to each other. Hence, the electromagnetic waves from one antenna element can get coupled into the neighboring antenna elements. Metamaterial based SRR, that is split ring resonator, can be used to block the electromagnetic waves and avoid the mutual coupling between the adjacent antenna elements in MIMO systems. Electromagnetic noise suppression. The planar electromagnetic band gap structures can be used to reduce the levels of noise, achieve signal integrity, and provide isolation in CMOS devices, mixed signal circuits, and systems. Non-invasive detection and microwave sensing. When any material is placed in the vicinity of microwave probe, the probe can be used to sense the properties of material provided that the material is placed in the near field radiation of that probe. The metamaterials can be also used for the application of evanescent field. Design of microwave components. Metamaterials can be used in the design of microwave components like waveguides, filters, power dividers, and phase shifters. Polarizer. The 3D anisotropic metamaterials can be used in the realization of narrowband and broadband polarizers. Metamaterials for improved performance in antennas. This is the case study. There are 4 steps in the case study. Step number 1. Study the frequency response of rectangular patch antenna using a MATLAB program. Second step. Study the dielectric response of rectangular patch antenna using a MATLAB program. Third step. By changing the dielectric material and the frequency of operation of antenna, do the performance analysis of patch antenna by simulating a rectangular microstrip patch antenna in Hypernix 3ED software. The purpose of these 3 steps in the case study is to study the degradation in the performance of rectangular microstrip patch antenna with change in frequency and dielectric material. The last step of the case study is a literature-based study of improved radiation in antennas using metamaterials. Frequency response of patch antenna. This is the frequency response of rectangular microstrip patch antenna. We designed a rectangular microstrip patch antenna operating at the frequency of 2.4 GHz with MC nylon substrate, the dielectric constant being 2.7 and the thickness of dielectric being 0.355 mils. We varied the frequency of operation of antenna in the vicinity of its resonant frequency, which is 2.4 GHz. When we changed the frequency from 2 GHz to 2.6 GHz with a step increase of 0.1 GHz, we found that there is a considerable decrease in the gain of antenna. Usually, the gain of antenna should increase with increase in frequency, but in this case, the gain decreases. What is the reason behind it? The surface of dielectric consists of dipoles, which is made up of a combination of positive and a negative charge. At high frequency, this dipole starts oscillating. Due to these dipoles oscillating, the dielectric tends to lose its property. The dielectric becomes lossy. The electromagnetic energy is radiated or leaked out from the boundary of dielectric material, because of which the electromagnetic losses occurs and the gain of the antenna or the overall radiation performance of the antenna undergoes degradation. Dielectric response of patch antenna. We calculated the various output parameters of rectangular microstrip patch antenna by using different dielectric materials or the standard materials used as dielectric. This is the tabular representation of the output parameters of rectangular microstrip patch antenna for different dielectric materials. Effect of dielectric material on the output parameters of patch antenna. This slide shows the graphical representation of the variation of output parameters with change in dielectric constant of the material. There is an considerable decrease in the gain and efficiency of antenna with change in dielectric. The characteristic impedance of patch antenna and the patch area also decreases with change in dielectric. As the patch area decreases, the amount of radiation from surface also decreases. Performance analysis of patch antenna. By changing the dielectric material and the frequency of the operation of antenna, we simulated a rectangular microstrip patch antenna and obtained its various parameters by using Hypernix 3ED software. The obtained results and their discussion is shown in the upcoming slides. VSWR plot. VSWR stands for voltage standing wave ratio. The standing wave ratio can be expressed either in terms of VSWR or ISWR, but it is usually expressed in terms of VSWR. The VSWR is the measure of how much amount of energy is reflected from load towards the source when we do the AC analysis by using transmission line model. The transmission line model is used to perform the AC analysis of patch antenna. It is found that the VSWR is minimum between
2.8 gigahertz and 2.9 gigahertz, which is very much closer to 3 gigahertz. That is the resonant frequency of that antenna. Thus, we see that when the antenna is operated at its resonant frequency, the VSWR has minimum value. The minimum value of VSWR indicates the minimum amount of energy is reflected from load towards the source. That is, there is a perfect matching of impedance between the antenna and the free space or antenna or the medium into which the antenna radiates.
Resonance curve of the antenna. The parameter Z11 represents the input impedance of the antenna at its edge. The input impedance can be divided into two parts, REZ11, that is real part of the input impedance, and IMZ11, that is imaginary part of the input impedance. The purple color curve represents the real part of the input impedance and the green color curve represents the imaginary part of the input impedance. Both these curves undergo a peak at a frequency which lies between the range 2.8 GHz and 2.9 GHz, which is very much closer to 3 GHz, which is the resonant frequency of antenna. Thus, we can conclude when the antenna is operated at its resonant frequency, the maximum value of the input impedance can be obtained. Radiation pattern. The radiation pattern is of two types, E-plane pattern and H-plane pattern. E-plane pattern consists of copolar components and cross-polar components, and the H-plane pattern consists of copolar components only. The copolar components are the desired components and the cross-polar components are the undesired components. The radiation pattern of the proposed antenna or the design antenna is of broadside type, that is, the maximum radiation will be perpendicular to the surface of patch antenna. Input impedance plot. When we change the frequency from 2.5 GHz to 3 GHz, the input impedance locus move in a clockwise direction, that is from left side to right side on the Smith chart, which shows that there is increase in the input impedance. However, when the frequency of operation approaches 3 GHz and it starts increasing, there is the reverse movement of the input impedance, that is the input impedance start moving from right side towards the left side, which shows that there is decrease in the input impedance. The input impedance plot on the Smith chart also shows that the maximum input impedance can be obtained at the resonant frequency of antenna. Current distribution on the surface of antenna. The current distribution on the surface of antenna gives the nature of polarization of the fields propagating on the surface of patch antenna. In the figure on right hand side, the density of current vectors in the upper half is more, while the density of current vectors in the lower half is less, which shows that the current strength in the upper part is more and the lower part is less. Moreover, the current vectors are aligned in one single direction from right side to left side, which shows that the polarization of the electric field is linear polarization. The left hand side figure also shows the current distribution, but it is the meshed structure. Gain enhancement in the patch antenna. The degradation in the performance of patch antenna with change in frequency and dielectric material was observed. However, this can be overcome by using metamaterials. By using metamaterial superstrates, that is magnetic split ring resonators, in combination with metallic patch, the gain and the bandwidth performance of the antenna is improved. The literature in the paper 4 states there is 17% increase in gain and the bandwidth of antenna by using metamaterial superstrates. Conclusion: the application of metamaterials in the field of wireless communication were viewed. The degradation in the performance of antenna with change in frequency and dielectric material was observed. The variant properties of metamaterials can be used to overcome the fundamental drawbacks and bottlenecks of antennas. The gain and bandwidth enhancement by maintaining the attractive low profile feature of patch antenna is possible by using metamaterials. Usually DNG type of materials, that is doubly negative materials, are used as superstrates in rectangular microstrip patch antennas. They have capability of absorbing electromagnetic waves generated on the surface of patch antenna and leaking from the boundary of dielectric, because of which the electromagnetic losses can be minimized and the gain profile of the antenna can be improved. These are some of the important references. Thank you.